Okay, so last class we've been talking about logarithmic functions. We particularly discussed how we found the domain of a logarithmic function. If we had the function itself, we just had to set the argument or the expression inside the parentheses of log, set that expression greater than 0, and then solve for x. And that's how you would find the domain. And we also learned how to evaluate logarithms utilizing certain properties of logarithms that we have here, these 4 properties, right? We also discussed the 2 very common logs that we use. One's called the common log, which is base 10, and the other one is called the natural log, which is the base is E, Euler's constant. And then we also saw how we can go from logarithmic form back to exponential form and vice versa. And we saw how we can transform the parent graphs of logarithmic functions, and how logarithmic functions and exponential functions, they're inverse relationships. They're inverse relationships of one another. So that's basically a nutshell of what we've done last class. And now we shall continue with some more properties, or in this case, we call them laws. So we have laws of logarithms. And I think this is a little... so you can disregard this whole statement here. That's a typo. You don't need that. So we're going to discuss 3 laws of logarithms. And these laws of logarithms are analogous to the laws of exponents. So what's the first one? So the first law is called the product rule, and the product rule states the following. If you have a log of any base, and inside the parentheses, the argument or the input, you have a product of 2 variables or 2 anything. If you have a product inside, then you can also rewrite this as a sum. So log of base of any base of xy, x times y, I can rewrite that as a sum of log base b of x plus log base b of y. This is like saying if you multiply 2 bases, right, that are the same, what do you do with the exponents? You add them. It's along those lines. And the same thing goes for log base b if you have a quotient, x divided by y. So if you have a quotient, you can rewrite this as a difference. Log base of x minus log base of y. All right. And then the last one, log base of x, I'm going to call it to the a value. So let's say I have x raised to some exponent. The power rule states that I can take out that a and put it in front as a multiplication. So these are my 3 laws of logarithms. And essentially, this is all we're going to be applying the whole time through as we see in these next few examples. So in the next few examples here, we have applying the laws of logarithms to evaluate. So I want to know, what does log base 2 of 1 over square root of 64, what does that result in, right? What does that give me? So the first thing is I have to rewrite the inside, right? I want to rewrite the inside somehow. So rewrite. How can I rewrite this? Well, one way is I can write this as log base 2. and rewrite this as an exponent, as a fractional exponent. I can write this as 64. Or actually, I can just say, what is the square root of 64? Isn't it 8? Don't we know that already? So I don't have to um I don't have to make anything more complicated. I can just simplify it immediately. So I got 1 over 8. Now, the problem is I want to see if there's a connection between 8 and 2. Can I rewrite 8 as some form of 2, some power of 2? And we can. So I can rewrite this as log base 2, right? Of 8 to the negative 1 power. And I don't know if you see this now. Remember, 1 over 8, I can rewrite this as 8 to the negative 1. And now, what do you notice? I got a minus 1 as an exponent or as a power. And look at this form. Look at this property or look at this law. This law has the same form here. So what am I going to do? I'm going to apply this law. So I'm going to apply law number 3. Apply law number 3. What does law number 3 say? Hey, put that exponent, put it out in front. So I'm going to have a negative 1 times log basis 8. I applied law number 3. And can anybody tell me what is log base 2 of 8 equal to? It's 3, right? Remember what log does? Log tells me what's the exponent that I raised 2 to get 8. Well, 2 cubed is 8. So log base 2 of 8 is 3. So the answer here is negative 3. Make sense? So that's how I was able to evaluate log base 2 of 1 over the square root of 64. That whole expression that we had here was evaluated by rewriting the inside, applying one of the laws here that was applicable, and then I was able to evaluate, simplify it, and get negative 3. Okay, great. How about so Daniel has trouble with Google Classroom. You can try again. There should be no problem with Google Classroom. I believe some people had trouble before with Google Classroom, but then I was given an email that they fixed the whole login issue. Just make sure you're using the CAMS account username and the corresponding password for that. Okay, Daniel? If not, then please email me if that doesn't work. Yeah. You have saved it to your computer. Yeah, that's kind of strange. So why don't you, Daniel, maybe email the help desk and see if they can help you with the login. Okay? Because it should work. And guys, just be mindful of all of your accounts and your passwords just for future reference, because that's important. There's so many accounts now, right? You have emails, so many different things. So make sure you know where those are, even if you save it, because Google is not so sometimes not so reliable. To tell you the truth, sometimes I get logged out too out of my accounts for no reason. I'm like, I don't know why am I logged out if I was logged in before. But that's why, personally, I don't save. This is just me though. I'm not saying do it, but I don't save any of my passwords to my computer. I don't. I keep them. Yeah. So Daniel, try to email your the help desk to see why you have an issue with that. Okay. And if they don't send you anything back within the next hour and a half or so, then I'll just have to email you the quiz, and they have to email me back. That's how we're gonna do it. All right. Okay, but you have to let me know, Daniel. Okay. All right. So let's continue. So we have 1/4 log base 3 of 81. So this one doesn't really require that much. I mean, we 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 can apply the law, right? So for example, here 1/4 times log base 3. So you should have an idea of 81. 81 is a power of 3. You can rewrite 81 as 3 to the 4th power. And then you see here, right? This here is one of those properties that we've discussed in the previous lecture. Or you could use law number 3 again. You can apply law number 3, which is what? Take the 4 and put it in front. So look what I get. This is law number 3 again, right? Law number 3. So you put it out in front, you get 1/4 multiplied by 4 times log base 3 of 3. But log base 3 of 3, log base 3 of the same number here is just 1. This is just 1. And so we get 1, but then 1/4 times 4 is also 1. So at the end of the day, I get 1. Okay. Now look at the next, so that wasn't too bad here. Now the third one, we have log 50, log 25, and log 8. And we have pluses in between. So this is where we have to look at the, how did we get 3 to the 4th? Okay. How did we get 3 to the 4th? Well, you have to have an idea prior of what these numbers are. So most of the time, when they ask you to evaluate using the laws of logarithms, right? These numbers that you get at the end as the answer are very nice numbers. They're usually whole numbers, right? So what that means is these numbers like 3 and the 81 here, there should be some connection between them in terms of powers. So you should already know, or you should have a list, for example, of all the powers of 2's. You should know what powers of 2's are. 2 to the 8th, 2 to the 9th, 2 to the 7th. You should know what those are or have an idea. The same goes for powers of 3. So when you look at 81 and you see a 3 here, you should already notice, wait a minute, 81 is a power of 3. And let's say you didn't know that. What do you know about 81? Don't you know 81 is a perfect square? So isn't 81 9 squared? So we know that, right? But then don't we know about 9? Isn't 9 3 squared? So isn't 9 3 squared squared? Isn't that what 81 is? That's another way you could have realized that 81 is 3 to the 4th. Okay? So it's good to know for your own benefit, powers of 2's. So 2 to the 4th. I think we have listed them before. Power of 3's, right? What's 3 to the 4th? 3 to the 5th, 3 to the 6th. Powers of 4's, powers of 5's, and powers of 6's. You should know these powers. Maybe not all of them, like, this goes on for it's a long list, but at least the first 4 or 5, or even the first 10 powers for each of those numbers, just to have a good reference. So 81 is a power of 3, 3 to the 4th. Okay, so now we're here, right? In this example here, we have a sum. We have two sums. So the idea is, which one of these rules are we going to use? Which one has a sum in it? And the only one that has a sum in it, thank you, Sydney, that's right, is the product rule. We have a sum. So whenever we see a sum, we're like, you know what? I can apply law number 1 here. So why don't we do that? Why don't we apply number 1? Law number 1. So law number 1 states the following. it means that log of 50 can be multiplied inside by 25. But then you notice, hey, I have another plus again. So I can apply law number 1 again. So when I do that, this is really what? Log of 50 times 25 times 8. And let's see what happens when I multiply 50 by 25 by 8. I get 10,000. So I get log of 10,000. Now, can anybody tell me what log of 10,000 is? That's right. It's 10 to the 4th power. So that's what you should perceive. You should perceive one thing. The first thing is log without any number in between and below, without any of these numbers here. This means that this is a base 10. So then you have to say, wait a minute, 10,000 is 10 to the 4th power, which means 10 to what power gives me 10,000? Well, it's 4. So the answer should be 4. So you see that? So log of 50 plus log of 25 plus log of 8, that gives me 4. And that's how I use the laws to evaluate the expression. I can combine the expressions all together because they're all sums. I can combine them into a single log where you multiply all the numbers, 50, 25, and 8, and I get 10,000. Okay? Great. So we didn't use all the rules. We didn't use a quotient rule, but we're going to use it in the next few examples here. Okay. So we're going to be doing something called expanding logs. So we're going to use the laws of logarithms to expand as much as we can the logarithmic expressions that we start out with. So I want to expand everything. So the first thing I notice is what? I notice that this is a quotient. This is a division. So I go back to my laws and see, hey, which one of these has a division inside? Well, it's law number 2, which is the quotient rule. So I'm going to apply the quotient rule here. So the quotient rule states the following. Take the log of a fraction, right? So if you have a fraction inside, then you can split it up as a subtraction, where this is the numerator and this is the denominator. So you get the following. You get log of y cubed minus log of the square root of 2x. So far, that's all I did. I applied the quotient rule, law number 2. But then look at those two logarithmic expressions individually. And what do you notice from here? There's a 3 in the exponent. Because this 3 has an exponent, I can place it out in front by the law number 3. So I'm going to apply law number 3 for this. So what does that mean? That means that I get the following. I get that 3 is in front, and I get log of y. So that's all I can do. I can't do anything further. There's no more laws to apply. So I'm done. But now, how do I take care of this one here? Well, you should know that the square root of 2x can be rewritten as the following. Log of 2x to the 1/2 power. So the square root is really raised to the 1/2 power. So again, what can I apply? I have an exponent again, right? A power. So I can place this in front of as well. This is law number 3 again. So then what do I get at the end? I get 3 log of y minus 1/2 times log of 2x. And can I do anything further from here? Am I finished with expanding? Well, there's one more thing I can do. If you notice, 2x is also a product. So this is a product. So I can apply law number 1. Now be careful here. This is going to be 3 log of y, right? Now I'm going to put a parentheses around this because the 1/2 is being multiplied, right? And I'm splitting this, but I still have this 1/2 in front. So I have to make sure I have a parentheses around. And then what's law number 1 say? We'll take the log of 2 and add it to the log of x. And then if you distribute that negative 1/2 after everything is split up as much as possible, this is going to be the expanded form of my original expression. And I am officially expanded everything. So that's what we're going to be doing that now from now on. We're going to be expanding as much as we can. So in this example, we used all the laws. We used law number 3 2 times. We used the quotient rule in the very first step, and then we had to apply the product rule. So we have to be observant and see if I can apply the laws more than once, when to apply them, and know when to stop. All right, let's look at the next one. So log base 2 of the square root of AB. So again, we're dealing with the square root stuff. Whenever you see square root or any kind of radical, rewrite as a fractional exponent. So this becomes log base 2 of AB raised to the 1/2 power. If this is raised to the 1/2 power, I can take the 1/2 and place it in front. So I get 1/2 times log base 2 of A times B. But A times B is another product. So because it's a product, I can split this up and make sure I put the 1/2 in front. So I get log base 2 of A plus log base 2 of B. And that equals 1/2 log base 2 of A plus 1/2 log base 2 of B. Okay? And that's it. I can't do anything further because each logarithmic expression just has a single variable in it, so I can't do anything else. So we're done with this. Great. Now next, ln of the cube root of x squared plus 4. Again, I have a radical. So because I have a radical, I have to rewrite it using the fractional exponents. So when I do that, I get ln, and I get x squared plus 4. This whole thing is being raised to the 1/3 power. Remember, this is the cube root. So the cube root can be rewritten as raised to the 1/3. So because it's raised to the 1/3, I put the 1/3 in front. And then I get 1/3 times ln of x squared plus 4. Now you have ln of x squared plus 4, and you might be tempted, hey, I can split this up as a sum, but I can't. Because x squared plus 4 inside, if you look at the laws here, there's no law that deals with a sum inside. The sum is on the outside. So if you have a sum inside, none of these rules are applicable. So we're actually done. We can't further simplify or expand. We cannot do that. So that's it. So we're done with this. That one didn't really require much, just one step. All right, are we good so far? Everything is okay? Any questions about expanding using laws? So the very last one here, we have log of 3x squared divided by parentheses x plus 1 to the 10th power. So the first thing we realize is what? This is a fraction. So the fraction I can split up by the quotient rule. So this is log of 3x squared. And when we do that, we have to subtract log of x plus 10, pardon me, x plus 1 to the 10th power. Okay. And then what else do I notice? I notice that this guy here has a product, 3x squared. So I can split that up as a sum. So this is log base of log of 3 plus log of x squared minus. Now, what do I notice about this expression here? I have a exponent inside, so I can apply the power rule or law number 3. So this 10 now can be placed in front. And I get 10 times log of x plus 1. And am I finished? I need one more thing, because if I notice, this guy is okay. But what about this guy here? X squared here has a 2. So this exponent can be now placed in front by the law of the power rule. So then finally, this is my final answer. Log of 3 plus 2 times log of x minus 10 times log of x plus 1. And I am finished. So this is how we expand logarithms, by utilizing the laws of logarithms. So any questions about these 4 examples here? Guess not. Okay, so we're good with this. So let's go on to the next segment here. And of course, we're always learning how to do one thing and then undoing it, or going in the reverse, right? So in the past 4 examples, we've been dealing with expanding logarithmic expressions. And now we're going to be combining them. So we're going to go backwards. So now we're going to be given an expression that's expanded, and we want to put it back into a single logarithmic expression. So again, we still have to apply the rules, but now we're going to apply them in the opposite fashion. Okay, so let's look at the first example. We have log base 4 of 6 plus 2 times log base 4 of 7. So what's the first thing you notice? You notice that there's a 2 in front of log of base 4 of 7. So what I'm going to do now, because this 2 is in front, I can place it back inside as an exponent, right? That's the power rule. So then what do I get? I get log 4 of 6 plus log base 4 of 7 squared. And then what's 7 squared? 7 squared is 49. So I can write this as log base 4 of 6 plus log base 4 of 49. And now I still want to put these 2 logarithmic expressions into a single one. So because we have a sum, we can apply the power rule, and I get log base 4 of 6 times 49. And then what's 6 times 49? 294. So this will be my final answer, log base 4 of 294. And of course, you can put this in your calculator and get a certain value numerically. But all we want to do is convert it from a expanded logarithmic expression to a single logarithmic expression, and we did that. Of course, that was the start of this, so this is a simple one. But now let's look at the next one. So again, what do we have here? We have 4 log x minus 1/3 log x squared plus 1 plus 2 log x minus 1. So I have a whole bunch of numbers in front of the logs, right? So that means I can put the 4, put it right back in. The 1/3, put it right back in. The 2, put it right back in. So then this is what I have. I have log x to the 4th, and then I have minus log x squared plus 1 to the 1/3 plus log x minus 1 squared. Okay, everybody with me with the exponents? I applied the power rule. And now what can I do? I got this minus, right? So what does that mean? If I have a minus, then I can put it as a, oh yes, we do the radical. That's right. We can treat this as a radical now, but we can do that at the end. We don't have to do that at the moment, but you can if you want. This becomes what? This becomes a single logarithm by putting it as a fraction, right? We get log of x to the 4th over, and then I can just make this into a square, the cube root. The cube root of x squared plus 1. Okay, so we recognize that this was a quotient rule, but I still have this plus here, right? I still have a plus log of x minus 1 squared. So because I have a plus, how do I treat it as a plus? What law do I use? I have to use the product rule. So I'm multiplying this, right? So I get this. I get log and I get one single log. I'm multiplying this expression with this expression. And this does not have a fraction. This does not have a denominator that you see. But obviously there's a 1 underneath. Whenever you don't see anything, there's always a 1. So when you multiply these two fractions, all you're really going to do is multiply this to the numerator. So this becomes x to the 4th times x minus 1 squared divided by the cube root of x squared plus 1. And that is my combined logarithmic expression into a single one. So I went from this whole expanded form into a single one. I applied the power rule 3 times. I apply the quotient rule once, and then I apply the product rule once. Okay, so for the next one, there's a typo I just realized. There should be a 5, but this 5 should be on the bottom. It shouldn't be at the top. So the 5 should be the base of log, not an exponent. Okay. Now what? So we have 2, and then we have a parentheses around it, log base 5 of x plus 2 log base 5 of y minus 3 log base 5 of z. So first, let's take care of the 2. Now be mindful that this 2 is applied to everything inside the expression. So let's distribute this 2 first. So what do we get? We get 2 log base 5 of x plus 4 log base 5 of y minus 6 log base 5 of z. Okay, now we have all the numbers that we need in front of the logs after we distributed this 2. And then what do you notice? Every one of these has a number. Every one of these logs expressions have a number in front of it. So this number can be placed inside back into the logarithmic function by the product of the power rule. So I get log base 5 of x squared, right? Plus log base 5 of y to the 4th minus log base 5 of z squared. So this 2 is placed inside here. This 4 is placed inside here, and this 6 is placed inside here. And then what do you notice? You have a plus, you have a minus. So then the sum here can be replaced as a single logarithm by multiplying them. And I get log base 5 of x squared y to the 4th. This whole thing is minus log base 5 of z to the 6th. And then what happens? I got a minus in between, and I can rewrite this as a division, as a quotient. So this becomes x squared y to the 4th over z to the 6th. And this is my single logarithmic expression. Are we okay with this? Good. Makes sense? Does this whole like application of product rule or the power rule and the product and the quotient rule, does this all make sense to you all? For the most part. Okay. Great. All right. So now we're going to be dealing with a lot more letters now, as you can see. And again, it's really about the rule itself rather than just the numbers. It's about the rule. So again, this also applies to natural log. It applies to any, the laws of logarithms applies to any log of any base. So natural log also applies. So here, what do we have? A sum, right? So this sum can be now split, put into a single logarithm by multiplying. So I get ln of a plus b multiplied by a minus b minus, and then what about this 2 here? This 2 here can be placed inside the log by ln c squared. So that's what I have so far. But does anybody know what a plus b times a minus b equals? What's a plus b times a minus b? Have you guys seen this before? So this thing inside here. What does this expression reduce to or simplify to? Chen, actually, yeah, there should be no middle term. It's actually exactly what Chao Fei says. It's a squared minus b squared. It's a squared minus b squared. It's the difference of perfect squares. Remember, a squared minus b squared is a plus b times a minus b. So if you multiply a plus b and a minus b together, you get a squared minus b squared. And this is minus ln of c squared. And then one more extra step. We have this minus sign in between, right? The logs, which means that I must divide. So this becomes ln of a squared minus b squared in the numerator over c squared, which is in the denominator. All right. So that's the single logarithm. And now we have the last one here. Log base AB plus C log base AD minus R log base AS. So the things that are in front of the logs, we put them back in. So what's in front of the logs? Well, there's a C in here, so I can place this as an exponent here, and there's an R here. I can replace this as an exponent here. So this becomes log A of B plus log base A of D to the C minus log base A of S to the R. Again, it's not so much about the letters, it's more about the rule that we're applying. So it could be anything in front. As long as it's in front, you can put it inside as a power. And for this example, we have a whole bunch of letters. But the rule still applies. And then this here is a sum, so that means I can multiply. So this becomes log base A of B multiplied by D to the C power minus log base A of S to dr. And then we have a minus in between, right? So if we have a minus in between, we can divide. We can divide what we have inside a log. So this is log of base A divided by B D to the C all over S to dr. And voila, we have our single logarithmic expression. Okay, so that's what we've been doing, right? We've been combining logarithmic expressions into single log, or we've been taking the single logs and expanding them. So we expand and combine. We expand or contract the logarithms utilizing these three laws of logarithms, or these three rules of logarithms. Okay. Okay. So now we're here. The change of base formula. So we have this expression here, log base x of y. Now the cool thing about this, about logs in general, is that even if I don't know, for example, the base that I'm dealing with, let's say I'm not too, like, we've been using a lot of log base 2, log base 10, log base e, right? What if I use another another base? What if I use log of 11, which is not really commonly used? Let's say I have something like this. Log base 11 of 45, right? And you're like, wait a minute, I don't really know base 11 like that. So how can I even get close to, like, how do I even fathom how to do this? Well, the cool thing is I can change this to any base, to the base of your preference. Let's say maybe you like base 2 more. I can change log base of 11 of 45 as log base 2 of 45 and divide that by log base 2 of 11. I can literally just say, hey, you know what? Let me just change my base. And this is going to be the same. Let's say I didn't like base 2. Maybe I like another base, maybe 10. I can literally write this as log base 10 of 45 over log of 11. Or let's say I don't like 10 or 2 either. Maybe I like E better. I can also write this as ln of 45 over ln of 11. And if you check yourself with your calculator, if you evaluate these expressions, you'll get the same value. So what is log base x of y in general? Well, I can choose my base b and say, you know what, this will be equal to log base b of y over log base b of x, where b is a chosen base. So the first example here shouldn't be too bad because we already know, right? We should already know what this is. This is 3. But let's say I didn't know. Let's say I didn't know. Let's say I want to, I know this is 3, right? But let's say I want to use ln, for example. Let's say I want to say that this is ln of 125 over ln of 5. If you put this in your calculator, and I would recommend you doing so, if you take ln of 125 and divide it by ln of 5, you do indeed get 3. So this is just to, this first example is just to verify that the change of base formula is true. It's not just something made up. So I can change my base to any base, which is cool. Now look at the next one. Log base 5 of 2 So then here, I'm like, wait a minute. What if I change this base 5 to 2, for example? Then I can write this as log base 2 of 2 over log base 2 of 5. Well, I know what log base 2 of 2 is. It's 1 because it's the same number. Now all I have to do is calculate log base 2 of 5. And can anybody tell me what's 1 divided by log base 2 of 5? Does everybody know how to use your calculator for this? You got a fraction? You should get a decimal. Yeah, so you should get a log. Yeah, so the decimal is 0.43067, right? And if you round it to nearest 4 decimal places, then you should get 0.4307. You see that? And let's look at the next one. Log base 6 of 92. I can rewrite this. Let's use base 10. So I can rewrite this as log of 92 and divide that by log of 6. So can anybody tell me what you guys get for this? Yeah, I got the same thing, Natalia. It's 2.5, 2365, dot, 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 right? And if you round this to the 4 decimal places, you get 2.5237. So these are little examples of how you can utilize other bases to evaluate logs of bases that maybe aren't as familiar, or maybe you just want to change the base for a reason. Yes, Natalia, ask away. What does changing the base do? Well, it gives you a way. Oh, when do you need to use it? Well, at this moment, you may feel like, hey, I don't really need it because, first of all, your calculator can deal with many different bases, but this is a formula that shows you the versatility of logs. So it's just for now. For now, it's just something that you can use. Okay. Um, Again, your calculator can do most of these logs anyways, but this is just something about logs that's true. You can morph into different bases. So maybe the utility of it or the benefit of it is not apparent as of now, but for now, just accept the fact that the bases can be changed to other bases, and you may or may not use this change your base formula when you have to solve equations, which we're going to do soon enough. Um, Maybe let me give you an example. Mm, Hmm. It's kind of hard to think of a good example here on the spot. But that's a good question, uh, Natalia. And a lot of these questions arise, right? Like, what's the point of learning this? Um, like, if you get into more complex logarithmic problems, the change of base is useful. And again, we use the base 10 a lot more, and we use base 2 more, and we use base e a lot more. So this idea of changing the base is extremely important when you have bases that you don't really deal with on a daily basis. Okay, so maybe right now it's not apparent. That's okay. But the idea is that because we're able to do so, some of our calculations will be simplified by changing the base. That's really it as of now. Okay, but that's a good question. All right, so we've talked about combining logarithms into a single logarithm. We talked about expanding them. We talked about this little change of base formula, which is uh, kind of cool that logs can be changed into different bases. And now we're going to go into solving exponential and logarithmic equations. All right. So here we have an exponential equation, and I want to solve for x. So we have 10 to the 2x minus 3 equals 1 over 10. So for this particular example, the good thing is that the base is 10. Okay? So I'm going to show you two ways to solve this problem. So solution number one. The first thing is I recognize, hey, I have a 10 as my base. And I also have a 10. I can rewrite the right side as a 10 in the base as well, except that now it's going to be raised to the negative 1. All right, so I rewrote 1 over 10 as 10 to the negative 1. And then what do you observe? You observe that you have the two bases that are the same, and there's an equal sign in between. So if two bases are the same and they're equal, then what must be true? It must be true that the exponents must be equal as well. It has to be. They have to be the same. So because that's the same, then we can say 2x minus 3 equals negative 1. And then we have a simple equation that we can solve, right? So we can add 3 on both sides. We know how to do this. This is 2x equals 2. So x equals what? X equals 1. So done. Or let's say you didn't know that. Let's say you want to just utilize logs. And do you notice that we can utilize logs here? The reason why we utilize logs is because my variable is an exponent. So whenever you have your variable as an exponent, use logs. Variable as exponent, use logs. Now, this is the case where you can use any log of any base. I can choose any base, and it works. However, which base makes more sense to use? Well, we're dealing with base 10, so might as well use logs of base 10. So if I do that, look what I can do. I can literally take log on both sides. And what do we learn about log base 10 of 2x minus 3? What can I do with the exponent? I can apply one of the laws, right, of the power rule. I can apply the power rule. And what does that mean? This thing goes in front, doesn't it? So we have 2x minus 3 multiplied by what? Log of 10. And then what's log of 1 over 10? Or what is log of 10 equal to? And what's log of 1 over 10 equal to? Well, log of 10, isn't that just 1? And log of 1 over 10, isn't that negative 1? So you see, don't I get the same exact equation? So I get the same exact answer. Sorry, so x equals 1. Did everybody see that? Does everybody see how we used log base 10? We could have used any base, but log base 10 make the more sense because my base was 10. Okay? All right. Same idea goes for the next one. Same idea. Where's my exponent? I mean, where's my variable? It's in the exponent. So I have to apply log somehow. So then what do? Solve for x. So I want to get x by itself, right? Well, first thing is subtract 8 on both sides then. And then what do I get? I get that e is raised to the 1 minus 4x. And this equals 12. What's the problem? I have this 1 minus 4x in the exponent. So then I need to get rid of that. I need to make that x variable no longer be a exponent, but be in front of, or be just a normal, where x would normally be, right? It wouldn't be an exponent. It would be a non-exponent. So then what do I have to apply? I would have to apply a log function on both sides, right? But what base makes sense to use? In this case, my base is e. So what kind of logarithm am I going to apply on both sides? I'm going to apply ln. Thank you, Tiffany. So I'm going to apply ln on both sides. And again, one of the properties of the logs is what? If I have the same base of the logarithm and the inside, in this case is e, and then this is also base e, then what does this become? This whole thing becomes just what? 1 minus 4x. You could also do the same thing we did in the previous example here, where we put this thing in front by the power rule, and then log base e of e, or ln of e, is just 1. So we get 1 minus 4x. Now, ln of 12 is a number, but for now, I'm not going to evaluate it. I'm just going to keep it this way. And I'm just going to solve for x. So I want to get x by itself, so I have to subtract 1 on both sides. And I get negative 4x equals ln of 12 minus 1. Still want to get x by itself, so I need to divide by negative 4. So I get that x is equal to ln of 12 minus 1 all over negative 4. So this is where you have to use your calculator. Ln of 12 minus 1 divided by negative 4. And the answer is negative 0.371226 ... Okay, so I want to say two things. This answer here, ln of 12 minus 1 over negative 4, this is called an exact form. This is an exact form. Why is it exact? Because there's no approximation. So this is an answer. You can literally leave your answer like this. But if you want an approximate form, then you have to use a decimal, so you use your calculator. So this is 0.3712. This is an approximate form. Why can't we evaluate 12 before the exact form? Would that change the answer? Okay, well, you can do ln of 12 beforehand. It's just that it will no longer be exact. The moment you plug in your calculator, ln of 12, and if you look at what ln of 12 is, 2.484906665, this number keeps on going forever and ever and ever. The decimal expansion goes on forever. The thing is, your calculator doesn't have an infinite number, right? It gives you a finite number. So it's already giving you an approximation. So the moment you put ln of 12 into your calculator, it's approximate. It's no longer exact. And so that's why I don't do anything until the end. If the answer that's required is an approximate form, then sure, you can evaluate ln of 12 beforehand. It's just that you have to be careful with the approximation regardless, right? Because if you do ln of 12 and you put in the first two decimal places, right? That's approximation. The moment you do an approximation here, the problem is you're still going to subtract by 1 and divide by 4. So you're dividing an approximation. So your answer will be an approximate of an approximation. So it becomes less accurate. So I would suggest always get to the exact form and then plug in your calculator so you can get the closest to the actual the exact form as possible. Does that make sense? Yeah. I know everybody wants to just put in your calculator and just get an answer. No, just wait until the end. All right. So we're learning how to apply logs now to equations to solve. Now look at the next one here. The next one here is a quadratic kind of equation. We have e to the 2x minus 2 times e to the x minus 3. Now look at this. I can rewrite e to the 2x. I can rewrite it as e to the x squared minus 2ex minus 3 equals 0. What do I notice? E to the x is being squared, and I also had just e to the x by itself. So this is where we use a substitution. So we say let u equal e to the x. If u is equal to e to the x, look what I get. I get u squared minus 2u minus 3 equals 0. What do I have here? I have a quadratic equation. And we've solved quadratics since the beginning of the semester, haven't we? So how do I solve this equation? U squared minus 2u minus 3 equals 0. How do I solve it? This should be 1, 2, 3, A, B, C. Three u minus 1u. Yeah, you could just factor this, can't you? Right, we can just factor. This is like the easy kind of quadratic equation factoring. So we can factor this as what? U minus what? 3, u plus 1, right? Don't these work? And then what do? We solve. U equals 3 or u equals negative 1, correct? But what was u though? What was u? U was what? E to the x. So I'm going to replace it with the actual e to the x because we're trying to solve for x. Now we're not trying to solve for u, we're trying to solve for x. So e to the x equals 3 and e to the x equals negative 1. That's really what u was, right? Now I want to solve for x and I got e to the x equals 3. So if I want to find x, then what do I have to do, for example, for this equation here? If e to the x equals 3, then how do I get x by itself? What do I need to do on both sides? No, not the square root, Andrew. We're not taking the square root for this. Remember what we've been doing in the previous two examples? we've been applying a specific step to make this exponent no longer an exponent. I have to do what? That's right, Damaris. I have to apply ln. ln. And what happens when you do ln of e to the x? What does that simplify to? What does ln of e to the x simplify to? Ln of e to the x equals what? Anybody? Ln of e to the x? Remember, same base? That's right, Tiffany. It's x. This equals x. So x equals what? Ln of 3. Done. You see that? That's it. That's it. And then if you want the decimal expansion, plug it in your calculator, ln of 3, and that gives you something. But again, that's in approximate form. This is exact. Because it's exactly what I meant to say it is. It's ln of 3. Now let's look at the next equation here. I do the same exact thing, don't I? I apply ln. But then what happens when I do that? What's ln of -1? Does anybody know what ln of -1 is? Well, if you plug in your calculator, what happens to your calculator? Error. There's an error. It's undefined. ln can never have a negative input. That's right. It can't exist. This undefined. So this doesn't work. There's no solution for this. So this equation has no solution. Does not exist. D and E. So then what's the only answer we get? ln of 3. That's the answer. And that's it. There's no other answer. All right. So that's how we solve exponential functions. I mean, exponential equations. We apply logs to exponential equations. In the next round here, we also have one more exponential equation here, but then we have logarithmic equations in the last two. Okay. So what do we have here? We have an exponential equation that we're going to solve by factoring. So what do we factor out? Well, we have a 2x and a 2x here. So I can factor out to 2x, and I get x squared minus 1. So this is a very strange equation. It's strange because we have an exponential expression, and then you also have a quadratic at the same time. So you're kind of like, wait, that's a lot at once. So this is what we have here. And then what do we notice about x squared minus 1? It's a difference of perfect squares, so I can factor that out as well. I get x plus 1, x minus 1. That equals 0. And then what do? I split all of these up, and I solve individually. So 2 to the x should equal 0, x should equal -1, and x should equal 1. Now, what's 2 to the x equals 0? Can I solve for this? Can I solve for 0? How do I solve? I mean, can I solve for x? How do I solve for x? How would I solve for x? This is also D and E, right? If I apply ln on both sides, or any log, if I use log, for example, log of base 10, for example. The very problem is log of 0 doesn't exist. There's no solution to this. So this is no solution. So then what do I say? I have only two answers, right? I got x equals -1, or I got x equals 1. So then this is plus or minus 1. And always check, okay? Always check. Check your solutions. And this will prove very useful. So let me just check. X equals -1. If I plug that in, I get -1 squared times 2 to the -1 minus 2 to the -1 equals 0. -1 squared is just 1. 2 to the -1 is a half. 1/2 minus a half equals 0. Check. X equals 1. 1 squared times 2 to the first power minus 2 to the first power. Does that equal 0? Well, 2 minus 2 does equal 0. So this also checks. So they will both work out. You always have to check just in case, because it might be a scenario where your x values that you get don't work. Okay? And this applies a lot to logarithmic equations. So if you look at the next one here, we have a logarithmic equation. Log of x plus log of x minus 3 equals 1. So I want to solve for x. That's still the name of the game, right? I want to solve for x. The problem is I have x kind of separated, and I can't get x by itself. I want to get x by itself somehow. Now, what am I going to apply here? I'm going to apply laws of logarithms. How am I going to do that? Well, look at this. This is a sum. What we're going to do is we're going to put them into a single log. So rewrite as a single log. So what does log of x plus log of x minus 3 become as a single log? It becomes log of what? X multiplied by x minus 3. Do you all see that? So the first thing I did is I rewrite as a single logarithm. And then number 2, what's number 2 going to be? Once I write it as a single logarithm, I want to get x by itself. Then I'm going to do what? I'm going to rewrite using exponential form. So this kind of is the opposite of what we just did with exponential functions. Exponential functions, we use logs. With logarithmic functions, you use exponential functions. You see how they are inverses of one another? So then how can I rewrite this, guys? How can I rewrite log of x times x minus 3 equals 1 as exponential form? What would be the exponential form for this? Well, remember, what is the base of log? The base of log is the base of log is 10, right? That's right, Andrew. So 10. And then what's the exponent? Remember how this works? This is 10. 1 is my exponent. So this is 10 to the first power. This has to equal what? It has to equal what's inside the log. So this is going to be x times x minus 3. Now, what kind of equation do I have here? If you distribute the x, what do you get? You get x squared minus 3x equals 10. You have a quadratic. I can solve this quadratic equation, can I? Set it equal to 0. So x squared minus 3x minus 10, that equals 0. Factor. This is x minus 5, x plus 2. So I get that x equals 5 and x equals -2. I get 2 solutions, but I need to check. And how do I check? With what do I check? I check always the original equation. Check with the original equation. So then what's the original equation when x equals 5? Does this work? Log of 5 plus log of 5 minus 3 is 2. Does this equal 1? Well, remember, what's log base 5 plus log base 2? It's log base 5 times 2, which is what? 10. And log base 10 of 10 is 1. This works. So x equals 5 works. Now, what about x equals -2? Remember, we always have to check the original equation. Log base -2 plus log base of -5. Does this equal 1? Now, what's the problem with having a negative inside the log? Do we know what log of -2 is? It doesn't work. That's right, Felipe. So this doesn't work. This is does not exist or undefined. It's undefined for both of them. So what do we say? We reject. This is no good. So the only answer here is 5. X equals 5. And that's the only answer. So even though I get 2 solutions for the quadratic equation, that does not solve my original equation. So always be mindful of your solutions and check them with the original equation, especially for logarithmic equations. Now the same thing goes for this guy, right? ln of x minus 1 plus ln of x plus 2. Put them as a single logarithmic expression. So I get log or ln. I get ln of x minus 1 multiplied by x plus 2 equals 1. Now I want to rewrite this. So this is going to be a little crazy. I want to rewrite this as an exponential form. My base here is e. My exponent here again is 1. And I get e to the first power is equal to x minus 1, x plus 2. Then when I expand the right side of the equation, I get x squared minus or plus x minus 2. That equals e. I still get a what? I still get a quadratic. Now this is going to be a little strange because when I solve this quadratic equation, I have to set it equal to 0. So I get x squared plus x minus 2 minus e equals 0. What happened to the 1? Well, the 1 is right here. But e to the first power is just e, isn't it? Well, Chen, I'm rewriting this as an exponential form. Remember how we did this in the previous class? We went from logarithmic to exponential form. So this is an exponential form. The base here is e, isn't it? It's e. And what's the exponent? It's 1. So e to the first power is this. That's another way to rewrite the logarithmic form to exponential form. And then we have a quadratic equation. How do we solve quadratic equations? Set it equal to 0. Now the problem with this is what? We have e in this quadratic equation. We have a irrational transcendental number. So we can't factor this. This is not factorable because there's no number that multiplies to -2 minus e that also adds up to +1 that I can think of. So that's a problem. We can't factor it, but that's okay because we can solve any quadratic equation as long as we know what? As long as we know the quadratic formula. So you have to apply the quadratic formula. Remember what the quadratic formula is? Negative b plus or minus the square root of b squared minus 4ac all over 2a. So to apply the quadratic formula, we need to know what? We need to know what a equals 1, b equals 1. What does c equal? What is c? C is the constant. And this entire thing here is a constant. Even though we have e in it, e is not a variable, it's a constant. So my constant is what? -2 minus e. Plug in the quadratic equation. So I get what? I get -1 plus or minus the square root of 1 minus 4 times 1 times -2 minus e all over 2 times 1. I get -1 plus or minus the square root of 1. Then I distribute, right? I need to multiply the -4 with the -2 and the negative e. And when I distribute, I get 1 plus 8 plus 4e over 2. So my answer is -1 plus or minus the square root of 9 plus 4e all over 2. So remember, I have 2 solutions. I have a positive one and a negative one. I got a positive and a negative. So I got x equals -1 plus the square root of 9 plus 4e over 2, and I get x equals -1 minus the square root of 9 plus 4e over 2. I have two solutions, but do both of them work? Well, I have to check both. Are you sure it's 9? Yeah. Unless I made a tiny error. I think it's 9, right? Because it's because you get -4 AC, right? So -4, I'm multiplying -4 with -2 minus e. So -4 times -2 is +8. And then you're adding the 8 with the 1, so you get a 9. Yeah. So you have to check now. You have to check. And is there any problem with this? Well, isn't one of them gonna not work? I don't have to do much to see that one of them doesn't work. Because remember, we have to check with the original, right? With the original equation. The problem is, if I plug this negative, this is a negative number, and I plug this number in here, into this x. So I have a negative number minus another negative. So this number here inside here, when I plug this in here, I get ln of a negative number. And what do you know about negative numbers for ln or for any log? It doesn't exist, right? So actually this becomes rejected. We reject this one. Yeah. So negative numbers inside ln, there's no good. But this one here, we can try also. And you can try this in your own calculators, and it should work. So if I get, let me, -1 plus the square root of 9 plus 4e divided by 2. Yeah, this should work because this number here is approximately 1.72896, so on and so forth. So if you subtract by 1, you're still going to have a positive number, so that's okay. And if you add it by 2, you're going to get a positive number. And if you plug it in your calculator with ln, it should work. It should give you 1. So you can check this on your own time. But this works. So the answer is just one of them. -1 plus 9 plus 4e all over 2. I'm pretty sure that's the first time you ever got this kind of solution for quadratic. But hey, this could be it. This could occur. There's no problem with that. All right, so we got 5 more minutes, and I think we should be able to do at least one of these. Okay, so we're going back to the applications of exponential functions. And remember, I told you we're going to go back to this compound interest problem. It says now the problem is no longer how much will it, well, we're going to find part 1. Part 1 here, find the amount after 3 years. We know that the man invests 5,000. The interest rate is 8.5%, and it's compounded quarterly. So n equals 4, r equals 0.085, and p equals 5,000, right? We know this. So then what is part A or part 1? A is what? P 1 plus r over n, nt. So this is going to be what? 5,000 times 1 plus 0.085 over 4, and it's 3 years. So t equals 3. So if you put this in your calculator, what do you get? You get 5,000 multiplied by 1 plus 0.085, 4, and this is raised to the 12th power. I get 6,435.09 cents. So you guys can confirm or not confirm, go against it, what I got here. But this is what you get after 3 years. So number 1, part A, is a simple compound interest problem. So everyone okay with this first answer? Okay. So that's the first one, right? But the second problem here is a different question. It says, how long will it take for the investment to double? So if I want my investment to double, I already know what the A value will be. If it doubles, then the A value will be 10,000, right? So my A value is 10,000. What I'm interested in is not what I get at the end, it's how long it takes to get there. So then this would become a different problem. This would be 10,000 equals 5,000 times 1 plus 0.085 over 4. N is 4. It's still 4, but then the question is T. T is unknown. You see this, guys? T is the unknown value. So T is my variable. So then what's going to happen eventually? I'm going to use logs to get what T is. So I want to find T. Okay. So to find T, I need to divide everything by 5,000 to get rid of this 5,000 here. The 5,000s go away, and I get 10,000 over 5,000 is 2. So I'm going to put this over here. So I get that 2 equals, and then let me just simplify this for you. If I simplify that, the stuff inside the parentheses, I get 1.02125. This is raised to the 4t. Now, how do I get that t down? I need to apply log, right? Let me apply log of base 10. Remember, I can apply any log of any base. So when I do that, I get what? I get log of 2. I'm not going to put it in my calculator yet because I don't want to mess up with the approximation. And this 4t now comes in front. This becomes 4 times t times log of 1.02125. Again, I'm not going to put the number in yet in my calculator. I want to get t by itself first. How to get t by itself? Well, I have a 4 being multiplied to it, and I have a log being multiplied to it. So might as well divide by 4 times log of 1.02125. And do that on both sides. 2125, right? So now these cancel. The 4 cancels with the 4. The log cancels with the log. And I'm left with t. T is equal to what? Log of 2 divided by 4 times log of 1.02125. And now you can put it in your calculator. Make sure when you write this in your calculator, you put parentheses around this guy, okay? A lot of people will make the mistake of not putting parentheses around the denominator. So this would be log of 2 divided by parentheses 4 times log of 1.02125. And I get 8.2410 . So how long will it take? It will take about a little over 8 years. So it will take over 8.24 years, approximately 8.24 years. All right, guys. So the same thing goes for compounded continuously. We use just a formula. It's just a different formula, but the idea behind applying logarithms is still going to be the same thing. All right.